In video 3-6, I'm showing you the mechanism for how you can really, in a slick way, use an acetal as a protecting group and then sort of reveal a mono. You're going from diprotected to monoprotected. Okay, so we show you how it's all about perspective, right? This is the molecule I am interested in. This is the molecule that is important to me. It's got a stereocenter in it. It's got two stereocenters, the alcohol and the methyl. And, I need to do some other chemistry, but I need to protect those alcohols from further reacting. So understand that you can protect a carbonyl as an acetal when the carbonyl is your interest, when this is what's important to you. Turn it upside down, though. I've literally just turned this molecule upside down. These are the same molecule. Okay, so here is here. I can add these methyl groups. So in one case, the thing that's important to me is the carbonyl, and I'm using an acetal to protect it. In the bottom case, what's important to me is the diol, and I'm using a throwaway acetone molecule to protect it. Okay, so you've got to understand that it's all about perspective. Acetals are protecting groups, but they can protect your carbonyl using a throwaway ethylene glycol, something cheap. Or you could have a 1,2 diol system, a 1,2 diol, and you could protect both alcohols at the same time using a throwaway ketone like acetone, like in a carbonyl. Okay, do you see the difference? All right, well, let's say that we have a 1,2 diol. That's what we have in this image. Okay. Oh, actually, we have a 1,3 diol in this image. 1,3s are fine too because you make 6-membered rings rather than 5. You don't want to go much more beyond that. Okay, so I've got a 1,3 diol and I want to protect both of them at the same time. A really interesting way to do that is to do a benzylidene protecting group. And it works the same way that we saw making an acetal. It's the same way because all we're doing is using this as the diol to make the acetal with the carbonyl. Okay? All right, we do that under acidic conditions. I've already showed you the mechanism. You can practice using this exact system if you want, but this is where we get to. We get to this protected system. Now, this is a twofer. It protects both alcohols at the same time. Okay? You can go on your merry way and do whatever else you need to do. But what's really cool about this, given what we know now about how alcohols of different substitution patterns, this one being primary and less substituted, and this one being secondary and more substituted, if I were to straight in and protect one over the other, the primary one is going to get protected first because that's the one that is less sterically hindered, right? So you would protect one, and then you could protect two, and then you'd have to remove P1 if you wanted to protect the secondary one and leave the other one open. It would take 3 steps: protect primary, protect the secondary, and then protecting the secondary would be a little tougher because it's even more sterically hindered now. And then you'd have to remove the protecting group selectively of P1. It's kind of a rigmarole. Alternatively, you could protect both of them in one step at the same time, forming the acetal. And then, in a really slick way, add dibal. Here's what happens. All right. Dibal is di, isobutyl, aluminum hydride. It has one hydrogen on it, and the aluminum, if you remember, is in group 3. It's very fickle. It doesn't have an octet. It thinks it wants an octet. It's going to be attacked by one of these very giving oxygens. And it's selectively, if you control your stoichiometry, if you only had one equivalent of dibal, I'm just going to write R's because I don't feel like drawing them anymore. The aluminum is selectively going to react at that position. Why? Because aluminum being attacked on this position, there's too much steric hindrance. So steric hindrance is going to drive the aluminum to be attacked by the primary oxygen. Okay? Therefore, in this next step, the oxygen here is going to assist in the down, out. Aha! What just happened here? Oxygen, double bond now. Aluminum, RR. So we've cleaved that benzyl away from the primary oxygen. The aluminum is still negatively charged, and you know what? It would love to dump that hydride somewhere. That's its weakest bond, so it's going to release the H-, so it can go back to its normal bond trend of 3 bonds. Where's it going to put it? Look, there's an activated carbonyl right there, right next door, intramolecularly. So this hydride, the H-, reduces the carbonyl. Basically forming this benzyl carbon with just 2 hydrogens on it now. It's simply a benzyl system. All that remains is to work up the system to remove the aluminum oxide bond. And what you get is now a benzyl-protected secondary oxygen and a free-to-react primary alcohol. Very slick.